As we consider ideal solutions, I actually want to step back a bit and go back to non-ideal gases and show that there is a way that we can treat non-ideal gases that we can imitate when treating non-ideal solutions that might be very helpful. So just to remind you, the Gibbs energy change, or I should say the partial of the Gibbs energy with respect to pressure, is just the volume. That's expressed in this partial derivative up here, and I've done this for molar amounts. Now, if we have an ideal gas, we have an equation of state we can use that relates that molar volume to pressure so that I can actually directly integrate this equation to find an expression for the change in Gibbs energy from some reference state, which I'll define as representing 1 bar, to some arbitrary pressure. And that would end up giving me this result here. I want to emphasize that this is good for an ideal gas, so this equation that we've been using fairly routinely is really only adequate or only appropriate if we're doing an ideal gas. So what if we have a non-ideal gas? How do we deal with that? What should we do? Well, of course, one of the things we're going to do is to define a new function. Why not? And we're going to define a function that's called the fugacity. And I apologize, I don't know where the name came from, and I don't know why it's continued to be used, but it is historical, so we're going to use it also. The fugacity is usually given the symbol F. And one of the properties of the fugacity that we're going to care about is that this fugacity is going to generally be a function of pressure and temperature, and that it will approach the pressure as the pressure approaches zero. So in other words, when we have a very dilute gas, a very dispersed gas at low pressure, then the fugacity is going to look like the pressure, and that also indicates that we are approaching, if you will, an ideal gas behavior at this point. All right, so the fugacity you can think of as being like the pressure. It approaches the pressure in a low pressure limit, but it includes non-ideal effects. So another way we could think of this is if we wrote down our expression for the Gibbs energy for an ideal gas, and I've written this above in temperature and pressure, that this is going to be the Gibbs energy of some reference state at a temperature and pressure of 1 bar plus RT log of the pressure over 1 bar. Okay, that's really just a re-expression of my result up here in the upper right. Okay, but now what we're going to do in the case of non-ideal gases, so now I want to express my Gibbs energy for a real gas at some temperature and pressure, and that'll again be equal to a reference Gibbs energy at a temperature and 1 bar. And I will tell you now that we're going to assume that this reference Gibbs energy and this are essentially the same reference state. All right, but now the issue of non-ideality is going to be incorporated in this new function, the fugacity, and I'll have a reference value for the fugacity. I won't necessarily assume that it's 1 bar, although we'll reach that conclusion a little bit later. So this is the transition we're making from basically an ideal gas treatment to a real gas treatment. And you'll notice that the power of this is that we basically have the same functional form. We don't have to learn a new equation. The only thing we have to do is, if we know we're dealing with an ideal gas, we need to substitute this function, the fugacity, in for the pressure when we do that. Now, we can actually relate the fugacity in various ways. We can relate it to the real pressure if we, for example, use the virial expansion. So let me show you what that is. And this is really just an aside. I'm not going to actually ask you to use the virial equation for anything like this. But you'll remember that the compressibility factor, okay, which was called Z, and Z was equal to basically PV over RT, but it could be written as an expansion. It should equal 1 when it's an ideal gas, but when it's a non-ideal gas, we'll have these additional terms. And we wrote it in terms of 1 over the molar volume. We can also write it in terms of an expansion in the pressure, which is what I'm doing here. But you can see that it basically incorporates non-ideal terms with these terms in this expansion. Now, if we use this, we actually can show, and I'm not going to actually do the demonstration, but we can show that this ratio of the fugacity to its reference state is equal to the ratio of P to 1 bar of the exponential of this virial expansion. actually without the first term, so it'll just be B2P times P plus B3P times P squared, and so forth. All right, now if our gas were ideal, these various virial coefficients would be equal to 0. And so then we would have that simply the fugacity was equal to the pressure. Now in that limit, as pressure goes to 0, if the fugacity goes to the pressure, then we must have that this reference fugacity also goes as 1 bar. So henceforth I'm going to treat F0 as 1 bar, the same as we do for pressure. All right, now that having been set aside, let's talk about how we might be able to relate the fugacity to pressure by using Gibbs energy and some additional calculations. All right, so let's suppose that we have a real gas, and this real gas is at a temperature and pressure that we're interested in. And what we're ultimately interested in doing is seeing what the conversion of this real gas is. I'm leaving a long bar to give myself some room, to an ideal gas at the same temperature and pressure. So that's what we want, and so if we can determine what this Gibbs energy change is for this sort of change of process, then we'll be able to get a handle on how to connect the ratio of fugacity to its reference state to the ratio of pressure to its reference state over here. Okay, much as we did here with the virial expansion. Okay, now we're going to do this by imagining a two-step process. The first of these steps would be to go to a real gas at a temperature and a pressure that approaches 0. Okay, and this will have a Gibbs energy change of delta G2. I might as well make these molar Gibbs energy changes while I'm at it. Okay, but if I have a real gas that's near a 0 pressure, that means the fugacity is going to the pressure as pressure goes to 0. So in other words, this is going to basically be equal to an ideal gas at that same temperature and that same low pressure. But now that I have an ideal gas, I can imagine a subsequent step that takes me up to the ideal gas at temperature and pressure, and that'll have a Gibbs energy change of delta G3 molar. So using simply the state function of state function property of Gibbs energy, I know that it doesn't matter how I go from my initial state to my final state, the Gibbs energy change will be the same. So these two quantities must be equal to one another. Now, although I'm adding this and I'm making a big deal out of it, how we actually calculate delta G1 is through calculating these two changes. I'm not going to physically do that here, but it involves doing these integrals from 0 to p of basically functions that look like the molar volume dp. Okay, so these are the sorts of calculations that we would use to determine delta G2 and delta G3. Now, I also want to point out that this Gibbs energy change of 1, we could write, technically, as basically the difference between the real Gibbs energy and the ideal Gibbs energy from these equations. But now the reference state here and the reference state here are going to cancel one another. So in other words, delta G1 bar is going to be equal to the ideal gas at temperature and pressure minus the real gas Gibbs energy at that same temperature and pressure. And if I take this equation up here at the top, that's just going to give me RT log of P over 1 bar minus RT log of F over F0, but we've decided F0 is 1 bar, so that'll be F over 1 bar. So now the final result of this is going to be log of P over F. Okay, and this is essentially going to give us what we need in terms of relating our fugacity to our pressure. Okay, in the limit of low pressure, of course, fugacity goes as pressure, so this would turn into 1, and we should expect log of 1, should expect this delta G to be 0 if I have ideal gas both here and here, but I don't. All right, so when we go through this evaluation of delta G2 and delta G3, what we'll find, essentially, is the following. We'll find that the log of P over F, which I told you was the thing that we were interested in, can be related to this following integral. It's the integral from 0 to p of 1 over p prime minus the real molar volume over RT dp. All right, so we've just integrated essentially these two steps to get to this. All right, now I'm going to define this as negative log of gamma, where this gamma is called the fugacity coefficient. And a lot of times it is easier to simply relate this fugacity coefficient than to talk about the fugacity itself. All right, so if I change this around, I want to get rid of the minus sign here, and I want to tidy this up a bit. It turns out if we use the definition of our compressibility factor, which I had used up here, but remember that Z is equal to PV over RT, I can actually write log of this fugacity coefficient is simply equal to this integral, Z minus 1 over P dP. All right, and these are things, this compressibility factor is something that we can determine experimentally, for example, and so we can do this integration, if not analytically, we can certainly do it numerically and get results for this fugacity coefficient. Now, notice that as we go to an ideal gas, so as we go to ideal gas, the compressibility factor is going to go to 1. If that goes to 1, then the integral goes to 0. And if the integral goes to 0, then our fugacity coefficient is going to go to 1. So this particular relationship is a handy relationship. I want to put a box around it because this is the result that we're going for here. This particular relationship then tells us how we might determine the fugacity for different things. And to just show you an example, and I will tell you we're not going to use this equation to do any calculations. I want you to be aware of the relationship here, though, and the fact that fugacity, while it seems like an exotic substance, is something that we can actually quantify. So just as a demonstration of this, if one were to quantify, for example, the ratio of fugacity to pressure, so for an ideal gas that would be 1, and do this over a wide range of pressures, we would find that it looks something like this for something like carbon monoxide. And this is a range over about 1,000 bars, okay? So this is not an inconsiderable pressure range. This is a huge pressure range, and this is ranging from about 0.7 to about 1.5. Okay, so the fugacity coefficient is something that is within the neighborhood of 1 much of the time at moderate pressures. So we'll find in practice that we won't be dealing with solutions that generate pressures of thousands of bar. So we'll be able to live in the ideal gas regime for most of our vapor pressures. However, if we do ever get into a system that needs the use of fugacity to treat non-ideal behavior, this means we have a way to do that.